So calorimetry is what we call the quantitation of thermal energy transfer. So quantitation of thermal energy transfer. So a kind of the easiest way to do these type of calculations is to look at what we call coffee cup calorimetry. And the reason it's called coffee cup calorimetry is in the lab we tend to use the cheapest insulated cups that we can find, are coffee cups. So I'm going to draw a double-walled cup, just showing that we're going to be insulated. We're going to fill it up with water. We're going to be able to measure the temperature of the water. We'll have a thermometer in here. Let's say we have an initial temperature of the water. We have a mass of the water. And we have the specific heat capacity of water. Let's see. And let's say that we take a block of metal. And we put it into the water. So what's going to happen is we have redraw our calorimeter with the metal block in. So we still have the water, but now we have the metal block. And so let's say that this metal block it has initial temperature as well, T initial. Now I'm going to say a common metal. So I have two initial temperatures that are different. This is mass of the metal and specific heat capacity of the metal. So we have different masses, different specific heat capacities, and different temperatures. Now, if we say that the temperature of the metal, so we have temperature water, temperature metal, and let's be more specific here, and say the initial temperature of the water, and give ourselves a little more room, and the initial temperature of the metal. And we're going to say that the metal is warmer. So we'll say that this is true. What that means is that the thermal energy from the metal is going to go into the water, because thermal energy always moves from the warmer body to the cooler body. In this case would be the water. Okay? And so the thermal energy would continue to transfer to the water until we reached something called thermal equilibrium. And that's when T water equals T metal. Now that's not going to just be at the average of the two temperatures. So if the water were 25 degrees Celsius and the metal was 75 degrees Celsius, thermal equilibrium necessarily will not happen in between those two temperatures at like 50 degrees Celsius. It depends on how much you have of each of the mass, as well as the specific heat capacity. Generally, metals have a much lower specific heat capacity. They can be warmed up and cooled down much faster than water. Okay? And so if we want to calculate how much thermal energy was transferred from the metal to the water, we can use the temperature change. So we can measure so we'll have the thermometer in here, and we can measure the final temperature. So we will have T final. Now T final would be the same for the metal and the water. So there's not two temperatures, just one. And knowing the final temperature, the masses haven't changed, the specific heat capacity haven't changed, we are able to calculate the energy transfer. And so how we do that is first we have to say that any energy that is transferred from the metal to the water, or that any thermal energy lost by the metal must be transferred to the water, not somewhere else. And so what we would say more generally is that the thermal energy lost by the system must go to the surroundings. Now, I put the negative sign on the surroundings, but it could easily have been on the system. You just need to have a negative sign on one side of the equation. We tend to put it on the right side by convention, but this is showing energy transfer. So this negative sign indicates energy transfer. It is going from one to the other. Okay, so in our particular situation, we would have, let's call our system the metal. So then we would have Q metal equals negative Q water. Again, it doesn't matter where the negative goes. Okay, and so we know that we can use Q equals MC delta T. So we can do this for each. And so I'm going to put in the mass, the specific heat capacity, and delta T for the metal and the water. And so we get, on the metal side, we get mass of the metal, C of the metal, and then delta T is T final, metal minus T initial, metal. And this equals, now this is the most important thing, you got to remember the negative here. I forget it all the time. You got to be better than I am. And so this is mass, water, C, water, and then T final, water minus T initial water. Oh, it's going to be close. We got it. Okay. Now, I'm going to do one thing here is I'm going to take this T final and this T final. I don't need a H2O there, but I'm going to put it in purple so we know that this is the same T final. And I'm actually going to get rid of this as well. So it's just T final here. And that is to show that we have the same T final in both. So, or that T final for the water and the metal is the same. Now, in this particular setup, we have 1, 2, 3, 4, 5, 6, 7 variables. So if you're given 7 variables, if I give you 6, you can find, if you're given 6, you can find the 7th. Okay, and so we can do this. For example, I could give you the mass of the metal. I could give you the specific heat of the metal, the initial temperature of the metal, and the water, and the mass, and the specific passive water. And I could ask you to find the final temperature. To do so, you would need to do some algebra to solve for T final, to isolate it on both sides and move it over and do some algebra. So these are problems that will do a lot to calculate and quantitate thermal energy transfer. So these are called calorimetry problems. So this is one type of calorimetry. The other type of calorimetry that we can deal with is bomb calorimetry, and this is actually a little different. This is called constant volume calorimetry or bomb calorimetry. So bomb calorimetry, also called constant volume. Constant pressure, we don't often call this type of constant pressure, but this would be open to external pressure, which would be atmospheric pressure. And so in bomb calorimetry, it's a little different. We have a container. This is generally a big experiment, and inside this container we have a chamber that's filled with water, and we put a bomb in there. It's actually like a solid tube this is our bomb. It's a reinforced tube, and we would put a sample in here. So we could put a sample, like we could take a slice of pizza, and let's say how many calories in that pizza, and we can actually do this. And so what we do is we fill it up with O2 gas, and now if you put enough, high enough amount of O2 gas, anything will combust. Anything. We only have about less than 10% of our atmosphere is actually I'm not sure the exact percent, but it's less. It's not a majority of our air is oxygen, and if it were, we'd all be exploding, which is nice that it's not, so we don't. But what happens is we basically combust, and that's why we get this called bomb. So we get thermal energy. Well, it's going into the water. I should do a little better there. So thermal energy goes into the water. And that would allow the water to increase in temperature, and we can measure that difference. So we can do this for chemical reactions, and this is how we can quantitate the exact amount of calories in pieces of food, or we could measure the exact amount of energy released for a chemical reaction. Now, the important thing, and the reason why we're talking about this, is that we have a slightly different equation. For example, if this were instead of a piece of pizza reaction, we would say that the reaction is our system, and that the surroundings is our calorimeter. Now, the problem with the calorimeter in the real world is that the thermal energy doesn't just go to the water, it actually kind of escapes and heats up the instrument. And so instead of trying to make a better and better instrument, to avoid this, what we can do is we can actually determine the heat capacity of the entire instrument. That is, how much energy does it take to increase not just the calorimeter, the water in the calorimeter, but the entire calorimeter. And so to do this, I need to explain a couple things. The first is specific heat capacity. So I'm going to compare and contrast. So specific heat capacity is given as a little c, and that has units of joules per gram times degrees Celsius. So for example, the specific heat capacity of water is 4.184 joules per 1 gram times 1 degree Celsius. So what this is saying is that it required 4.184 joules to raise 1 gram of water 1 degree Celsius. So the larger the specific heat capacity, the more energy it takes to change the temperature of 1 gram of water 1 degree Celsius. So it's specific for an amount of water. Okay, as you have more water, it takes more energy. Scales up or scales down. So this is specific heat capacity. We could also just have heat capacity. It's not specific. And this is a much more general term. Heat capacity is a uppercase C. I know that's confusing. Sometimes some books will use a little s here, but I use little c. And the heat capacity is given in joules per degree Celsius. Now, the mass is removed. And so the heat capacity, the difference is you can determine the specific heat capacity. This is provided in tables. So this doesn't change. It is the same. In each situation, the heat capacity is given, or is not given, it is experimentally determined each time you do an experiment. So this is actually going to change depending on the temperature of the air in the room, the temperature of the instrument, many variables go in this. So each time an experiment is run. So if you do calorimetry in the lab, you're probably going to determine the heat capacity of your coffee cup calorimeter, not just use the specific heat capacity of water, because it's not actually as insulated as we pretend in these general calculations we do in lecture. Okay? And so because we have no grams, then what this looks like, if we come back here and we say Q calorimeter, then it would be Q reaction is equal to negative big C of the calorimeter delta T is equal to Q reaction. Okay, and so we determine the C calorimeter experimentally, and we have delta T that we can determine the change in temperature of the water. Okay, and so we can often then determine from the Q reaction, we can determine the delta H value, and if we have the number of moles of what was reacted, then we can get a joules per mole value. So there's a couple ways we can do this. Often, how we find the C calorimeter is that we first use a delta H reaction for something like a known substance like benzoic acid. In lab, we would do this, where we know So we know the exact delta H reaction of a substance. That's easy to calculate. We then react benzoic acid in our bomb calorimeter. We measure the temperature, and then we calculate the C calorimeter. Then, knowing the C calorimeter, we can then have an unknown chemical reaction to measure what that might be and measure the delta T. So, in these types of problems, you always have to determine your heat capacity, uppercase C, using a known reaction or reactant, such as the combustion of benzoic acid, for example, or something like that, to determine the experimental value of the heat capacity. So, moral story is specific heat capacity that we would use for like water is known. The heat capacity for a calorimeter or an experimentally like a coffee cup calorimeter in the lab, you would determine that where you do not have perfect insulation, you would use a calorimeter or heat capacity. So where there's no mass provided. Okay, so that's the difference between specific heat capacity and heat capacity. I know it's a little confusing, both in letters and names. I apologize, I did not come up with this, but just know that in the lab, in real life, we use heat capacities. In lecture, we tend to use specific heat capacities because we can assume things are perfectly insulated and everything's fine. We can't do that in the real world.